Hello, I'm Dean Klober, and welcome to my online seminar. Today I'm going to discuss the method of stabilized amplitudes in quantum field theory. In a nutshell, the objective of this research is to enhance our physical understanding of how an elementary charge and radiative processes in QFT modify the vacuum. This will lead to a very simple formula for computing finite scattering amplitudes. And in the process, I believe we'll gain insight into why QFT predictions agree so well with experiment. So let's begin with a little background. Our primary focus is going to be on radiative corrections and the divergences that arise when we sum over intermediate states of high-energy virtual particles. Back when I was a graduate student, I was studying quantum electrodynamics. And I walked into my advisor's office one morning, and I mentioned to him that it looked to me like radiative corrections did not conserve energy. Well, do they? Take the electron self-energy in QED, for example. My advisor pointed out that the Feynman rules conserve 4 momentum at each vertex, but arbitrarily high momenta circulate in the loop, and the scattering amplitude, sigma of p, diverges logarithmically as the energy cutoff, lambda naught, approaches infinity. And that means that an infinite negative mass energy must exist so that we obtain the expected rest mass energy. And it's not accounted for in this basic Feynman diagram. Now, renormalization attempts to fix the issue by assuming a bare mass, m naught, such that m naught plus the electromagnetic mass gives the observed mass. But we have to ask, where did the energy for this process come from? Well, there are more issues. After mass renormalization, you still need to renormalize the wave field. That's also known as external line renormalization. And then for the photon self-energy, you need to redefine the charge. Here, in addition to the vacuum polarization, we include a photon propagation function to obtain an expression that's accurate to second order in the electron charge E. But we have an infinite part, Z3. Now the renormalization method absorbs that infinity into the physically observed charge, where E naught is a bare charge that's assumed to begin with. And here pi hat is the finite part of physical interest. Then for the vertex, you need yet another subtraction of infinities. So the root cause of the problem has not been identified. It's just hidden in mass, charge, and wave field renormalizations. Now, early researchers were highly skeptical of all this. Feynman called it an awkward process, and Schwinger said that the theory was incomplete. Well, that was in an early paper back in 1949. But I believe that the statement is still true, as I hope to show in the coming slides. And Dirac went on to say that it wasn't really a mathematically logical process. It was just a set of working rules. But nowadays, the divergences are widely viewed as non-problems. Well, the predictions are in remarkable agreement with experiment, and renormalization group ideas have eased physicists' concerns. However, let's take counsel from the patriarchs of the theory, do a little bit of our own thinking, and see if there's some underlying physics yet to be understood here. And that brings us to our purpose, which is to propose a resolution to divergences in QFT that yields expected finite amplitudes without renormalization. The basic problem is that standard QFT neglects important vacuum energy changes, and that violates conservation of energy, and it does not account for all mass states in loop diagrams. Our solution approach is to first apply energy conservation. We'll identify a complete set of mass states for the particle vacuum system. And finally, we'll define a stabilized amplitude, which includes an opposing probability part involving intermediate mass states dressed with vacuum energy. The advantages of this method is that it has a sound physical interpretation. It's mathematically simple, and fundamental particle properties like mass and charge are rock-solid constants. So let's get to it. We'll go back to undergraduate E&M, and we'll assemble a classical charge from infinitesimal parts. Now the work done equals the energy in the resultant electrostatic field. And we'll assume that the agents that do the work draw energy from a well. After all, it's got to come from somewhere. Then the energy of the complete system is a constant if we include matter, the electrostatic field, and the energy well. Looking at the final assembled charge on a spherical shell of radius A, we have the electrostatic energy in the region R greater than A. And the energy of the well is just depleted by that electrostatic energy. So the total energy is just a finite constant. Now let's try to generalize this idea for an elementary point charge. We have two independent systems, a stable charged particle E and the surrounding vacuum phi. And we'll assume that the net vacuum energy is zero. The charge draws negative energy from the vacuum, which is an equivalent way of looking at it. And the positive energy density in the surrounding region is attributed to the observed EM field. In this case, the electrostatic field energy, E squared over 8 pi. Now, to uphold energy conservation, we need to account for the vacuum energy deficit. And the whole process may be visualized as a redistribution of vacuum energy by the core electrical charge. Now we can write a stability condition on the vacuum energies, and equivalently one on the electromagnetic masses. And it may appear that little has been accomplished, since we can simply add the physical mass m to both sides of the equation and identify the bare mass as m plus a mass deficit, MEM minus. But we could have just as well associated m with the electromagnetic mass. So we begin to suspect that the bare mass is just half of the story. If we opt to proceed with the bare mass only, then we introduce an asymmetry, and we encounter the aforementioned issues with the theory. So let's take stock. We have a core mechanical mass M and two electromagnetic masses, a self-energy and a mass deficit. Now in quantum mechanics, it's important to have a complete set of states to adequately describe any physical system. In this case, we need a complete set of mass states. So we really have three mass states, including two dressed core mass states. These are localized transient states dressed with positive or negative vacuum energy. And these will become important when we consider their insertion in the internal fermion lines of this electron self-energy diagram, for example. More generally, infinite field actions lead to dressed mass states. And the fermion self-energy is just equal to its corresponding scattering amplitude evaluated on the mass shell. Now here we introduce a scaling factor, eta, which multiplies the physical mass, mf. And we notice that the expectation value of the dressed mass over mass levels, lambda equal plus or minus 1, is just equal to the physically observed mass. Now, what are the dressed mass states for bosons? We have the charge W and the neutral Z and the Higgs boson. Well, let's apply electroweak theory and see what those dressed mass states are. Now our assumption is that the Lagrangian is invariant under an average over DCM states. Recall that the electroweak Lagrangian has gauge, Higgs, and fermion parts. And the fermion part, LF, is linear in MF. And the Higgs part is linear in the square of the boson mass. So by inspection, we see that we recover the dressing rule for fermions. And for bosons, the dressing rule just depends on the squared masses. And the square of the boson self-energy is just equal to the boson scattering amplitude evaluated on the mass shell. So the boson self-energy is just equal to a scaling factor eta times the boson mass. Now let's move on to generic self-energy and vertex processes. For these three diagrams here, the blobs contain irreducible insertions, which in general involve photons and other particles in the standard model mass set, blackboard M. The incoming momenta for BSE and FSE processes become dressed in the blobs and may involve off-shell terms. For the vertex, the momentum transfer is invariant under a DCM transform. Okay, what about these irreducible graphs? Well, they contain no self-energy or vertex subgraphs. They're proper. They don't break into two graphs by cutting an internal line. And they're primitively divergent. They become convergent upon cutting an internal line. And with symmetric integration, all these graphs have logarithmic divergences. The ones outlined in blue here are the types of diagrams we're primarily concerned with, and we'll represent those by a scattering amplitude omega. Now we also have improper diagrams and reducible diagrams. And these diagrams are important when we need to consider more complex processes, but they can always be evaluated once we know the answer for the irreducible diagrams. So let's keep this question in mind. Where does the energy for irreducible processes come from? Now let's consider mixing. For bosons in FSE and vertex processes, the bosons dress in the same manner as the fermions. Similarly, for fermions in BSE processes, the fermions dress in the same manner as the bosons. And these are just consistency requirements, which follow from inspection of the scattering amplitudes. Now the SM mass set that's dressed with vacuum energy is just equal to a scaling function, eta sub lambda, times the undressed mass set, blackboard M, where eta sub lambda is just defined by the dressing rules. For radiative processes, the interaction region is similar in size to the Compton wavelength. For example, the Compton wavelength, lambda sub c, defines the effective range for bosons in the Yukawa interaction model. And for fermions, cross-sections are proportional to lambda sub c squared in Rutherford or Compton scattering formula, for example. Now we have two regions of physical interest, depending on whether the particles are dressed with vacuum energy or not. First, we have the far field, which is a spatially extended region with a radius comparable to the Compton wavelength, lambda sub c of m, where m can be either a fermion or a boson. Now for FSE processes in QED, the factor kappa here is just 1, and the energy ranges from the physical mass m up to our cutoff lambda sub naught. For BSE or vertex processes, kappa is 2, and the energy limits are just doubled. And these details follow from integral expressions for the scattering amplitudes. Next, we have the near field, which is a point-like region containing ultra-high energy particles. And relative to the far field, the radius of the near field is reduced by our scaling factor, eta. And the dressed masses are confined to the near field. Okay, now let's put it all together and assume that an irreducible process omega borrows energy from the vacuum, creating a system of high-energy virtual particles in the far field. Then to conserve energy, we require a parallel process, omega bar, which opposes omega and accounts for mass states that are dressed with vacuum energy in the near field. And we can represent this in a diagram for electroweak processes. But for strong interactions, all we need to do is to interchange the energies that were borrowed from the vacuum in this diagram. And the sign of the stabilized scattering amplitude is just reversed. So let's see how this occurs. Now we've already considered how an electrical charge draws negative energy from the vacuum, leaving a positive energy in the surrounding region A. The situation is just the opposite for a color charge in our model, which is a sink for positive energy, leaving a negative energy in the surrounding region B. So for color charged quarks and gluons, they're enclosed in a negative energy color field, and there's a negative probability of detecting them in the far field. And we can represent this mathematically by letting psi be the probability amplitude for finding a particle, and it's indexed by L for a lepton, or S for a quark or gluon. Then the norm of psi sub s is just -1 in the far field and +1 in the near field, just opposite the case for a charged lepton. Now the near field is a point-like region, and it would take a probe of infinite energy to detect a particle there. And we can evaluate the expectation value of the squared momentum operator for a quark or a gluon, and it's just -p squared for space like p in the far field. Now we can summarize the method of stabilized amplitudes. The stabilized scattering amplitude, omega hat, ensures conservation of energy, and it accounts for all intermediate mass states. And the dress core amplitude just involves an average of omega evaluated at the dress mass states, where we take the limit as the scaling factor eta approaches infinity. Now just a few notes on the evaluation of the near field or dress core amplitude, omega bar. Mass ratios in the scattering amplitudes are invariant under DCM transforms. And the momenta input to a loop go on shell. We can see this because in the divergent integrals we encounter expressions of this form, which evaluate to the mass shell values. Also for cutoff regularization of the divergent integrals, the cutoff scales in the same manner as the masses. Now let's look at our basic QED radiative corrections. The stabilized amplitudes are finite and they agree with renormalization and experiment. This is shown in detail in Appendix C of Reference 11. At the bottom here we have the DCM rules for dressing the internal fermion lines of these three diagrams. Now let's take a closer look at the stabilized photon self-energy in QED and consider an infinite number of corrections to the photon propagator. The overall modification is given by a multiplicative factor Z3 hat of k squared, which involves a polarization function pi hat of k squared. The leading diagram here actually consists of three diagrams, one for the core mass and two for the dress mass levels. We can define an effective coupling constant and equivalently an effective charge, but the elementary charge is naturally defined on the mass shell, where k squared is equal to 0 and pi hat is 0. Z3 hat. I call it that because of the correspondence with the renormalization constant Z3 in the standard theory. But Z3 hat is finite, and there's no renormalization in this approach. Let's develop a more general verification employing the QED vertex as a prototype. We expand the core amplitude, lambda mu, in a Taylor series. And the first thing to notice is that lambda mu is dimensionless, and the dress derivatives vanish as our scaling factor eta approaches infinity for n greater than or equal to 1. Averaging over the dress mass levels, lambda mu bar is just equal to L gamma mu, where L is a well-known divergent expression involving a standard divergent integral d naught, which depends upon our cutoff lambda naught. Also notice that L is invariant under these DCM transforms. So, the stabilized amplitude involving these three diagrams is finite. Now let's consider boson self-energy processes and their verification in electroweak theory. Here we have a number of Feynman diagrams which contribute in second order, including the photon self-energy, gamma-Z mixing, Z boson, and W boson self-energies. Let S equal to the squared 4 momentum and construct the stabilized amplitude sigma hat. The core, or unrenormalized amplitude, is given by Hollick in reference 12. To evaluate the dressed core amplitude, sigma bar, we expand the core in a Taylor series. And we find that only the first two terms of the expansion survive when dressed with vacuum energy. The higher order derivatives, evaluated on the mass shell, vanish for n greater than or equal to 2 when dressed. From the stabilized amplitude, it's easy to show that sigma hat and its first derivative vanish on the mass shell. And these relations are equivalent to the usual renormalization conditions. For fermion self-energy and vertex diagrams, we construct the stabilized amplitudes. And using the expansion method, we evaluate the dressed core amplitudes. And we easily obtain the stability relations, which agree with the usual renormalization conditions. For QCD, we applied the stability method to evaluate 7 diagrams, including 3 baseline diagrams, which are simply related to QED amplitudes by a group factor. We also have the gluon self-energies in the pure gauge sector and a quark 3 gluon vertex. Collecting these results, we can define a running coupling constant, where alpha sub s is the experimentally determined value of the strong coupling constant when rho sub s is equal to 1. Here K is space-like and ms is a reference mass. For a switching factor, lambda sub s equal -1, we recover asymptotic freedom. And this is a key result which vindicates the physical interpretation. Let's take a closer look at the pure gauge sector to understand how the reference mass arises in the stabilized theory. Since the gluons are massless, we have no obvious mass reference. But the gluon carries color charge, and vacuum energy is redistributed in our model. The solution here is to introduce a small mass, mu sub g, in the gluon propagator. Then mu sub g becomes dressed with vacuum energy in the near field amplitudes. And we can define the gluon self-energy as our scaling factor, eta, times mu naught, an arbitrary unit of mass measure. Then if we require the polarization function to vanish on the mass shell, similarly to the photon self-energy in QED, then this fixes ms in terms of mu naught. Now in the standard theory, ms is chosen somewhat arbitrarily to be the Z boson mass. However, in the stabilized theory, if we synchronize momentum arguments for diagrams in the pure gauge sector with those involving a mixture of quarks and gluons, then we can derive an estimate for ms in terms of the quark masses. Now mz is approximately 91 GeV over c squared. And ms, computed in this way, is about 71 GeV over c squared. So we're in the ballpark of acceptable masses. In summary, the stability-based formulation yields renormalized amplitudes in agreement with experiment. We verified this for single loop diagrams in both electroweak theory and quantum chromodynamics. And we conclude that renormalization is only needed in standard QFT because the core scattering amplitudes neglect near-field vacuum energy changes in violation of the law of conservation of energy. And it does not account for virtual mass states that are dressed with vacuum energy. The signed dress core amplitude is localized in a point-like near-field region, and it opposes the core scattering amplitude, as indicated in this table. Since the S matrix represents a transition probability amplitude connecting initial and final states, we believe that this is the solution to the problem of infinities in quantum field theory that Feynman was seeking, as he alludes to in reference 4. So, the stabilized amplitude, omega hat, accounts for redistribution of vacuum energy, and the physical constants are really constant. Here we give a list of the references that were cited in the presentation. And if there are any questions or comments, feel free to drop me an email or leave a comment below on this platform. And finally, thank you very much for tuning in to my talk, and I really hope you enjoyed it.